Array reversal. I mean, it sounds like a completely basic concept, doesn't it? But today, we're going to get this explained. Whether you're gearing up for a tough technical interview or just looking to write more elegant code, we're going to strip away all the confusion. We'll look at exactly how the experts handle this kind of data manipulation. Let's get into it.
Okay, so here's our roadmap for this explainer. 1. What is array reversal? 2. The temporary array method. 3. The pro two-pointer approach. 4. Iterative versus recursive reversal. 5. Built-in language tools. And 6. Best practices and mistakes. Let's jump right in.
Starting with Section 1, what is array reversal?
Quite simply, array reversal is just the process of taking a list of elements and flipping their order entirely. So if you've got an array sitting there with 1, 2, 3, 4, 5, reversing it obviously gives you 5, 4, 3, 2, 1. And yeah, while it sounds incredibly basic, mastering this foundational concept is exactly what leads to much more advanced problem-solving skills down the line. We're talking things like efficiently checking for palindromes or setting up really complex sorting algorithms. It's also super common in real-world applications. Think about producing reporting dashboards in reverse chronological sequence or presenting data in descending order based on a user's criteria. It's literally everywhere.
But here is the real puzzle. And honestly, this is exactly the kind of provocative challenge an interviewer is going to throw out there at you. How do you reverse an array in place without using extra memory? I want you to keep that constraint in the back of your mind as we look at our very first solution.
Moving to Section 2, the temporary array method. This is basically our brute force baseline. So, this is often the very first solution developers reach for, and the steps here are highly intuitive. First up, you generate a brand new temporary array that perfectly matches the length of your original one. Second, you set up a loop to iterate through the initial array backwards, so starting from the last index and counting down to 0. Third, you transfer those elements into the front of that temporary array. And finally, you copy the newly ordered items from the temporary array all the way back into the original one. Honestly, it's incredibly easy to wrap your head around. Simple, right? But costly. This method requires O of n space complexity because you are explicitly creating a second array. And you might be wondering, why does this actually matter? Well, if you're processing a massive data set, like we're talking millions of records, using extra space essentially doubles your memory footprint. That is a massive disadvantage when memory consumption is a strict priority for your application. Which brings us to Section 3, the pro two-pointer approach. Now, what's really interesting about this is, instead of creating a whole new array, we do this sort of symmetrical dance with the data we already have. Here's how it works. You set up 2 pointers, one at the very start of the array and one at the very end. Then you just swap the values at these 2 positions. Once you've done that, you move both pointers inward toward the center, incrementing the start, decrementing the end. You repeat this swap until the pointers meet or cross in the middle. And here is a really cool realization. If you have an odd-length array, that exact middle element naturally and perfectly stays in its original place, completely untouched. Because we're doing this entirely in place, the space complexity drops to a beautiful O of 1. We are only using a few integer variables, typically an I and a j, to track our positions. And that is regardless of how massive the array is. It's an absolute game changer for computational efficiency.
AlgoMonster's deep dive on this sums it up perfectly. They say, the beauty of this approach is its symmetry. We process the array from both ends simultaneously, completing the reversal in exactly n over 2 swaps. You see that mathematical symmetry right there? That is exactly what elevates this from a beginner's script to a true pro-level technique.
All right, on to Section 4, iterative versus recursive reversal. Let's talk programming paradigms.
Now that we've got the core logic down, let's explore how we actually write it out in code. When we look at these 2 main paradigms, iteration operates with constant extra space. It's incredibly fast and it carries absolutely 0 risk of a stack overflow. Recursion, on the flip side, involves a function repeatedly calling itself with shrinking start and end pointers. Now, while recursion breaks a problem down cleanly and elegantly, it relies heavily on call-stacked memory. So if you try to recursively reverse a massive array, those function calls grow right along with the array size, creating a very real risk of deep recursion and nasty stack overflow issues.
So, the crucial point here, your pro tip, is to prefer iteration over recursion for this specific task. While recursion is amazing for things like tree traversals, the standard iterative loop is your safest, most efficient default choice for everyday array reversals to avoid all that extra overhead.
Now, let's look at Section 5, built-in language tools. These are your real-world cheat codes. Because out in the real world of production code, we don't always have to write these algorithms from scratch, right? Most languages totally have you covered.
In JavaScript, you can use .reversed, which actually mutates the original array right there in place, or you can use .to reverse it if you want a safe, shallow copy. In Java, if you're working with an array of objects rather than primitive data types, you can quickly convert it to a list and use collections.reverse. And in Python, you've got options too. Calling .reversed modifies the list in place, while array slicing with bracket ::1 creates a really fast reversed copy. Just keep in mind that while Python's slicing is incredibly fast to write, it does create a copy in memory, so it's not strictly an in-place mutation.
Finally, Section 6, Best Practices and Mistakes.
Because knowing how to write the algorithm is only half the battle. Knowing the traps, that's what makes you a true pro. Let's look at a few common pitfalls. First up, incorrect swap indices. If you're using a standard for loop instead of the 2 pointers, it is super easy to accidentally try swapping I with the array length -I. Since arrays are 0 indexed, that's going to throw an error. You absolutely must use array length -I-1. Second trap, skipping elements. If your loop boundaries are even slightly off and you don't iterate exactly to the midpoint, you might overwrite data or leave the middle elements completely untouched. And finally, forgetting those edge cases. Always add a quick check at the start of your function to immediately return if the array is null, entirely empty, or only contains a single element. It saves processing time and, more importantly, prevents unexpected crashes.
So we've covered the basics, the memory considerations, and the pro-level algorithmic techniques. But I want to leave you with a bit of a provocative thought. Let's say you have an array of 100 items. How would you use that 2-pointer approach to reverse only the elements from index 20 to 50, leaving the rest completely unchanged? Think about how you'd set those boundaries. Thanks for diving into this explainer with us, and happy coding.